What is a first-order low-pass filter? We have a noisy input signal like the one above. To the human eye, we can see what the temperature is, but we need to smoothen this data to a signal like the one below so that, say, a microprocessor can make sense of it.
Instead of diving into the mathematics head first, I'm going to start with some intuition building by talking about a jug of water that is a thermal inertia. Then I'll tie it in with a more familiar resistance capacitance or RC circuit and talk about the associated mathematics. Let's say we need to measure the temperature of this stream of water. The problem is that it's got a lot of noise, but we want a smooth and filtered signal like this. So how could this be achieved? One idea would be to introduce a jug of water in the middle. The input signal is noisy, but it mixes with a large body of water, so we get a filtered signal coming out. This is the logic of a low-pass filter. The inlet temperature is, say, T in. The temperature of the jug of water itself is T. Assuming perfect mixing, the exit temperature will also be T. Assume that this jug is perfectly insulated. Let's say the jug is made up of many small elements. The area of each of these rectangles represents the mass of the element. Assume that we are sampling our system at a cycle time of delta t. If the mass flow rate of water is m dot, and I stack that up as the length of one of the sides of these rectangles, then for the area of this rectangle to represent a mass, the other side will have to be the sample time delta t. So if I multiply the two, m dot star delta t will give me the mass me. At the end of the first time step, the temperature of all of these elements is even because of homogeneous mixing, which can be represented as capital T. At the second time step, an element enters the jug and we lose the same amount of homogeneously mixed water in the same time step from the jug. The mass of all of these elements in the pink box is at a temperature T from the previous time step, which I shall denote as m subscript m. The total area, therefore, is capital M, which is the sum of m subscript m, and the element mass, which is m subscript m plus the mass flow rate multiplied by the sample time. The input temperature is T in, and any noise in the input water, or the input signal more generally speaking, gets effectively divided amongst all of these different element masses. Then the question is this: once the new element mixes in, what is the new average temperature of this jug of water? This average temperature is the filtered temperature and can be calculated as the weighted average of the temperatures of all of these elements. That would be the contribution of the input element, me over m multiplied by its temperature, and the contribution of the water that was already in the jug, m subscript m over the total mass multiplied by its temperature. To get this equation to a more generic form, I'll replace the denominator, that is the total mass, by the sum of its elements, and then I'll divide by m dot. I'll tell you why I'm dividing by m dot later on in this video. I will summarize this section by saying the low-pass filter value is simply a weighted average of the input value and the filtered value calculated in the previous time step. On a side note, this idea where the output is calculated based on the output from the previous time step is called recursion. Therefore, the low-pass filter is called a recursive filter. So here is a simulation of the equation we just simulated. This is the input. It is a step input with some noise thrown in, right? So this is a bunch of high frequency noise, and we're looking to smoothen this out. This is a simulation of the water jug itself. So this is the input, and it's got some high frequency noise, and you can see that it's a lot smoother out here, and there is a bit of lag. The input flow rate is at 0.1 kilograms per second, and currently the jug is at 0.2 kilograms. Let's see what happens if I make that, say, 1 kilogram. So you can see that this has become a lot smoother. The penalty is that we have got more lag out here. So this is because of what is called as phase lag, but now it's a lot smoother. Now, what if I made this value 0, right? So keep in mind that this value mm that I'm changing out here, this mass of the jug, this is all of the this is the mass of all of the blue squares except for this one dark blue square out here. So except for the input, this is the mass for the rest of it. So that's the measured mass mm. That's what I'm changing out here. So if I make that 0, what happens, right? Effectively, I'm removing the jug. So it's just going to become a straight stream of water. And if I run this, you can see that this just nullifies the filter. And then I can turn it back on. Let's just say I'm going to make this, say, whatever, 0.5. Okay, so now filtering is back up. So what do we learn from this? The larger the capacitance, we get a smoother signal. This is what a low-pass filter is.
If you would like to learn how to make Simulink models like this, then check out this link on the top right corner of your screen.
Now let's describe the same equation from first principles. As we are concerned about the evolution of temperature, we need a formula for T dot. Dimensionally speaking, this is temperature over time. Multiply and divide by joules to get joules per time in the numerator divided by joules per degree Celsius. Furthermore, I can multiply and divide by kilograms in the denominator. Joules over time is watts, that is power. So the numerator is net heating power divided by thermal capacitance multiplied by mass. So this is the difference between the heat content of the water entering and exiting whole divided by specific heat times mass, which we can simplify into the following equation. This equation is in continuous time. We need to now convert it into discrete time. Let each one of these blue boxes be samples. We need to calculate the new temperature based on temperature from the previous sample. The sampling time is represented as delta T. We previously derived this equation for the rate of change of temperature, which can also be approximated as the difference in temperature across samples divided by the sample time. Now we substitute in the total mass equation and rearrange. We get this equation. This is the exact same equation as we got using geometry. Now let's compare this with an RC circuit. I'm not going to be deriving the equation here. You can look it up. It's pretty common. You can see that both of these equations have got a pretty similar structure. We can take the coefficient of our independent variable as a, this term as b, and this term as x. And we get an equation of the form x dot is equal to minus ax plus b. I now want to solve this equation. I can achieve this by multiplying e to the power of at on both sides and integrating. We can apply the product rule on this term as it is the differential of e to the power of atx. We get e to the power of atx on the left hand side and an a in the denominator on the right hand side to account for the exponent. Now let's add the integration constant and move across Euler's term. We still need to get the value for c, our integration constant. We can substitute at time equal to 0, x equal to 0 to get a value for c as minus b by a and substitute this back into our original equation. I want to now show you how the output of a low-pass filter changes for different values of a. Consider these samples. This is our equation on the top left corner. When a is equal to 1 by 2, e to the power of minus at takes the following form. You can see that we reach round values of exponents at multiples of 2, and these are its values. Now the term 1 minus e to the power of minus at takes on the following values, or in other words, x reaches 63.2% of its final value in 2 seconds and 98% of its final value in 8 seconds. When x is equal to 1 over 3, we get a similar pattern of values. Instead, x reaches 63.2% of its final value at 3 seconds. What this means is that the inverse of a drives when x reaches 63.2% of its final value and therefore It's called the time constant and commonly denoted as tau.
Visually speaking, we've got two low-pass filters of time constants 2 seconds and 3 seconds for the same step input. We reach 63.2% of the final value at 2 seconds and 3 seconds respectively, and 98.2% at 8 seconds and 12 seconds respectively, which is 4 time constants. Now I want to loop back to something I mentioned at 3 minutes and 50 seconds of this video.
I said that I would explain why I had divided this equation by m dot. It is because this term right here, this is the inverse of a, which is the time constant tau. So if I substitute it back in, and if I take the coefficient of t in here as alpha, then the coefficient of t, that is the temperature from the previous time step, becomes 1 minus alpha. This gives us a really clean equation because what it is telling us is when tau is high, that is when our time constant is high, alpha is small. So the contribution of a fresh input signal is low, and we will mostly be carrying forward the value of the output from the previous time step. Conversely, when the time constant is low, then alpha is higher and we will be relying more on a fresh input signal. Finally, I want to talk about the Laplace transform of the low-pass filter equation. Let's take our equations for the electrical circuit and the thermal inertia. I can replace these terms by 1 over the time constant to get the equations as such, and rearrange, and finally apply the Laplace transform. I get an answer of the output over the input as 1 over tau s plus 1. You might be wondering why I did not start with this, because this is probably how you are studying about it in school. Well, it's because it's unfortunately not a very illuminating explanation for people approaching the subject for the first time. And why is it called a first order low pass filter? It's because only the first differential features in the equation, and therefore first order.
I will be posting more videos about control systems engineering, so please like and subscribe this video so that it shows up. Thanks for watching.